Hello, everyone. So we're going to get on with a lecture here, and this is gonna kind of be the almost second half of calculus, if you will. So really, calculus boils down to two things. Derivatives is the first thing, and we spent a lot of time on derivatives. And what we're going to be talking about now, and for the rest of the course, will be the second part of calculus, which is integrals. And so this lecture here on integrals is really, it's actually going to be split into four parts. Each part should be pretty short, but I split them up that way because this idea of integrals when it's first introduced, it can be very complicated to think about. So I break it up into four parts so that after each part, you can kind of, slow down, think about what's happened, just in that part and really focus in on that. And so just before we actually get started in talking about an integral, I'm going to give a very loose definition of an integral. It's kind of the opposite of a derivative. So we've learned how to take derivatives of several different types of functions. We've learned sort of methods for derivatives, power rule, or excuse me, product rule, chain rule, quotient rule, things like that. And the functions we've used maybe the power rule or the exponential rule or a logarithmic rule. For our derivatives. And with integrals, we're going to do a lot of the same stuff, but it's going to be going backwards. It's going to be going in reverse. So basically, just for a very quick example, we might have f of x is equal to x squared. Well, if you were to take a derivative of that, you would say that f prime is equal to 2x. And so what we've done here is we've gone from the function to the derivative. Well, what we're going to do with integrals is we're going to go backwards. We're going to go from the derivative and find out what the function itself is. And actually, we'll see this, but another word for integral is antiderivative. It's not as commonly used, but that word antiderivative really just says, hey, it's kind of like the opposite of a derivative. So let's go ahead and get into this idea of integrals. And building up to a definition, I want to actually talk about derivatives and do a little recap there. So recall derivatives here, and I'm going to use d dx notation here. So I'm going to use d dx of x cubed is 3x squared. So this is me just doing the power rule right here. Nice and simple. We've got the power rule right there. And then here on this second example, this is an exponential, as you can clearly see. And you'll notice here that I am using the chain rule in this exponential part. I do have a 5x up here. So since that's not just an x, you can kind of treat it like an inner function that I've boxed right there, 5x, and an outer function, which is that exponential, that e. And so I do have to multiply by the 5 there, and that's my chain rule term right there. And then lastly, we might have a logarithmic derivative here. And again here, I am using the chain rule. It doesn't explicitly show up, but 3x right here. So because that's not an x, I do have to do the chain rule. But I'll let you go ahead and work out that derivative to see that you do, in fact, just get 1 over x. So anyways, these are our derivatives here. These are common derivatives that we should be comfortable with at this point here. So when we talk about an integral, what we're going to do is, instead of me giving you the function and saying, hey, take a derivative, what I'm going to do is I'm going to give you sort of this answer, if you will, and say, hey, tell me what this is. Tell me what that is. Tell me what that is. I'm going to say, hey, tell me what the function was that I took a derivative of. So I'll tell you 3x squared, and you're going to have to come up with, okay, in order to get 3x squared, I must have taken a derivative of x cubed, and then x cubed would be your answer. So that's going to be integrals. What I want to do here is I want to actually focus in on this exponential rule right here, and I want to do some algebra with this. So this is a true statement. We've got d dx of e to the 5x is equal to 5e to the 5x. So I'm copying it down, and then that chain rule 5 that we have right there. So this is a true statement. But what's going to happen more often than not is, rather than me asking you, hey, so I'll go ahead and actually explicitly write this out, like take the derivative of 5e to the 5x. Rather than me writing that down, more likely what I'm going to say is take the derivative of e to the 5x. And so, and really what I'm getting at here is that this is kind of our simple function. This is like, hey, oh, and excuse me, I don't want to say derivative. I want to say integral, which again, I haven't really defined explicitly yet, but I've kind of hinted that it's going backwards. So don't worry, we'll get to our explicit definition in a second. But really what I'm getting at here is that and we'll see this when we look at examples, but this is more common than this right here when I ask you to take the integral. Just like the same way when I ask you to take a derivative, I'm just going to kind of give you this basic function right here. I'm not going to necessarily give you something more complicated like 5e to the 5x. I just kind of want that basic like, hey, e to the 5x, let's take an integral of it, and maybe even I go as simple as just saying, hey, I've got e to the x, and let's find like a formula for that. And we'll get into all that later. But really what I'm getting at here is if I asked you to take the integral of 5e to the 5x, you could very clearly see, all right, given what's written right here, the integral of this is going to be e to the 5x, right? And so that's going to be that answer to this question in the red. But if I say e to the 5x, this doesn't really help us because I don't just have explicitly an e to the 5x on this side. So what I can do is I can actually do some algebra to this, and I can actually divide both sides by 5 right here. So you see I get a 1/5 on this side. And then what I can do is I can take this 1/5 and I can bring it to the inside. And that's just using the constant property of derivatives. We've seen that before. So that should be pretty comfortable. We're used to seeing that as taking this and pulling it out of the derivative, but what I'm going to do is I'm going to actually bring it in to the derivative. And so this is a true statement as well. Take a minute to let that soak in, where this right here and this right here, they're both true statements, and really they kind of say the same thing. I've just divided this 5 over and brought it in. So at this point here, now I can answer that question, hey, what's the integral of e to the 5x? What's the antiderivative? If I gave you e to the 5x and I said, hey, that's my answer, tell me what I took a derivative of to get this, you would be able to respond with 1/5 e to the 5x. And that would be your answer right there. So with this, I've kind of said this enough. Let's actually get into the definition. I've said integral enough. Let's actually go ahead and get into a definition. And this is going to look a little weird, but keep in mind that it's just saying the integral of this is just whatever goes in here. The integral of the circled function is just whatever the boxed function is. Just like you might say, hey, the derivative of the boxed function is the circle. We're just going to say it the opposite way. We're going to say the integral of the circle is the box. So definition wise, this gets a little confusing because I'm going to use a capital F and a lowercase f. So keep in mind through all of this that little f is my original function and capital F is the antiderivative of it. It's the integral. So if I say, first off, that capital F prime is equal to little f, what that means is that if I take capital F and I take a derivative of it, then I get little f. So for example, capital F is equal to x cubed. Well, then f prime of x is equal to 3x squared. So what I'm getting at is that little f of x, I'm going to also call that 3x squared so that we can very clearly see that capital F prime and little f are the same. So that's a true fact. Then what we say is that this capital F, this x cubed, that's the integral of this little f. So basically by making this sort of connection here between capital F prime and little f, it's just saying that the integral of little f is capital F right there. What we write when we say this, obviously we don't want to just write out the sentence like every single time. So we have this integral symbol here. It looks like a long sort of squiggly line and elongated S. Actually, this is a capital S in Greek letters, sort of elongated out. You'll see this written a lot with the sigma right there, similarly. But anyways, what we write notation wise is, and I'll read this out as I go along through this, the integral of f of x dx is equal to capital F of x. Now, I have not explained at all what this dx is or really what this integral sign means or anything like that. Don't worry about that. This is just sort of notation and what we're seeing here. But basically, when you see something like this, that's just telling you that, hey, the integral of this function is this function right here. So what I might write is I might write out the integral of 3x squared dx is equal to x cubed. And what we're seeing here is, let's go backwards with it. Hey, x cubed, if I take a derivative of that, guess what I get? 3x squared. So that means that if I take 3x squared and I take an integral of it, I get my x cubed. This right here is kind of the same idea as in derivatives when we might write d dx of x cubed is equal to 3x squared. When we write this out, what I've got here in the red, it's explicitly saying, hey, here's my function x cubed that I'm taking a derivative of. And when I do a derivative of that, I get a result here of 3x squared. And that's exactly what this is saying. I have a function 3x squared, and when I take an integral of it, I get my result x cubed. Again, don't worry about this dx. But so these should look fairly similar in terms of sort of their format. There's some sort of calculus operation here, whether it's an integral or a derivative. And then there's a notation that describes what function I'm doing that calculus on, and then my answer and the result that I get there. So there we go. So what I want to make very clear, and I'll go ahead and skip right over that. What I want to make very clear here is that both of these mean the same exact thing. So I've been doing this with these polynomials. Let me go ahead and write that out, just sort of adjacent here. So the derivative of x cubed is going to be 3x squared. And then x cubed is equal to the integral of 3x squared dx. So I am writing this guy sort of backwards, if you will, but that's fine. It doesn't matter which thing is on which side of the equal sign. So this is the sort of example I've been dealing with mostly, but it works here as well. What I mean here is what's in these boxes. Let me go ahead and box these. So the things in these boxes are the same thing. They mean the same thing, but it depends on if you're talking about these things in the context of a derivative or an integral here. And so if I told you that the derivative of 1/5 e to the 5x, or if you calculated it and you got e to the 5x, what that means is that, hey, the integral of e to the 5x is going to be 1/5 e to the 5x. So those statements mean the same thing. And I won't bother writing this out because this will take a long time, but sort of imagine some air quotes of me saying the derivative of x cubed is 3x squared. That statement is perfectly equivalent to the integral of 3x squared is x cubed. They really just mean the same thing there. Yeah, so with all of that being said, we've seen this sort of definition of integrals. We've seen some examples here. We've kind of talked about how they're the opposite of derivatives. My biggest way to actually just get the sort of concept of integrals nailed down is to just do examples. And just continually doing examples, you'll start to get very comfortable with this notation. I'm not going to worry too much about what this dx is for now in this part of this 4-part lecture, but we'll get into that later. So just kind of pretend, just not pretend, but keep it there, keep writing it down. That's okay for now, not understanding why we have a dx there, but that's okay. Here, let's just go ahead and look at these 6 examples. So the first that I want to do here are these polynomials right up front. And well, first off, we've actually done this one over and over and over already throughout this lecture. It's very easy to see that if I take x cubed and I take a derivative of this by the power rule, I'm going to drop my 3 down, and then I'm going to subtract 1 from that top, giving me 2 up there. Well, I drop the 3 down, and then I end up with a 2. That's 3x squared. So rather than saying, hey, the derivative of x cubed is 3x squared, now what I'm saying here is, hey, if I ask you to take the integral of 3x squared, you're just going to tell me x cubed. Same thing goes here for this 2x. I'm going to have x squared. And so take a look. If I take this 2 and I drop it down in front and then subtract 1, then that gives me 1. So I have 2x to the 1, which is just 2x. Oh, voila, we got it. So the integral of 2x is going to be x squared. What I want to make note here, and we'll see this in more detail, but I just kind of want to point this out. And let's take a look here. Actually, what I'm doing here is I am adding 1 to that, and then whatever that result is, which in this case is 3, I'm dividing that by there, and that actually gives me my x cubed. Same thing here. I have an x to the 1 here. If I add 1, that gives me 2 up on the top, and then if I divide by 2, that gives me x squared. And we'll get more into that. That's actually going to be the power rule for integrals, but we'll get more into that later. Let's go ahead here, move right on down to this guy right here, e to the x. Well, we've seen before that the derivative of e to the x is e to the x. So just flipping that statement around, the integral of e to the x, well, it's just e to the x. And I know this might look weird, but think about it. If I asked you to take a derivative of this, you would say e to the x. So that just goes right there. This is a perfect example of where it doesn't change. Just like in a derivative, if you add e to the x, it doesn't change. Same thing with an integral. Now here's where we got to be. Here's where we got to be a little bit careful. We got a lot of 2's and 2e to the 2x all here. So when I see this, for now, what I'm thinking about is pretty much just, it's just a guessing game. It's just like, all right, I got to come up with a function such that when I take a derivative of it, I get this. And so it is very backwards thinking, but that's kind of how these integrals work for now. We'll get more explicit in rules and things like that in later parts of this lecture. But for now, we're kind of just guessing. So when I see this, I see, hey, there's an exponential. So I know that there's got to be an exponential somewhere in here, because with derivatives, we always copy that exponential down. So because I'm going to copy that exponential down, if I was doing a derivative, let's just copy it here. And this is just me guessing. So I've got e to the 2x, and this is a good point where I would say to myself, I'd say, hey, let's check our answer. Let's just see if we're right or if I need to adjust it at all. Well, if I take a derivative of e to the 2x, and let's go ahead and actually write this out. So if I take a derivative of e to the 2x, just like our derivative exponential rules state, I'm going to copy that exponential down, but then chain rule dictates that I have to multiply this by the derivative of 2x, which is just a 2. And right here, I'm seeing, hey, look, the derivative of e to the 2x is 2e to the 2x. So flip that sentence. The integral of 2e to the 2x is e to the 2x right there. And so this actually, we got it. And we kind of just use this guess and check method, but we really just said to ourselves, we sort of made an educated guess, and we said, hey, I see an exponential here, and with derivatives, I just copied it down, maybe did some chain rule and things like that. But with derivatives, I started by just copying that down. So why not just copy it down here? And then it just worked all of a sudden. That's a lot of what happens on these integrals sometimes. It's just guessing and checking. Right here, this is kind of just a formula. This is just recognizing, what we've seen before. We've got ln of x here. If I take a derivative of ln of x, I get 1 over x. And that's something that we should know by now. So going backwards, going the opposite way, if I take an integral of 1 over x, that gives me ln of x. And there we go. Here, again, it's kind of just this. This is an exponential. Don't let this ln confuse you. This is not a logarithmic scenario. The x right here, the variable is in my exponent. So this is an exponential case. And again, it's kind of just that same idea of let's guess and check like we did up here. So I see the 3 to the x. I'm just going to try just 3 to the x, and let's see what happens. So let's go backwards. Let's take a derivative of this. And when you take a derivative of 3 to the x, you'll recognize that you get exactly this right here. So that actually confirms that the integral of this is that. Now, let me be clear here. These examples have been very simple. They've kind of worked out perfectly, especially these two right here, where I just kind of said, hey, let's make an educated guess and just, think that maybe these are our answer. And oh, look, they work. Well, a lot of times that won't happen. And really, what if this isn't a 2? Or what if this isn't an ln of 3? What if I change those constants out front? What if I change these even harder? And for now, I don't really want to focus on that. I just kind of want to show sort of the magic of how this works and how in these cases it can just a simple guess can just give you the answer. Obviously, these will get harder, but we'll deal with those in future parts of this lecture. But for now, we'll call that good, and just make sure that these examples feel really comfortable before moving on to the next part. And there we go. That'll be the lecture.